we get to the two new kinds of chi-squared. You guys did chi-squared. You read chapter 26 for homework. And questions 7, 8, and 9 on the just checking, okay, we went ahead and you were asked to decide whether or not it was either homogeneity, goodness of fit, or independent. So you should, based on your answers for the just checking, know the difference between the three. Okay? So let's kind of take a step back for a minute and decide what is the difference between the three. So based on what you read and what you know, tell me when you use each one of them. Okay? So we have goodness of fit, we have homogeneity, and we have independence. So give me something that you already know. Devin, give me one thing.
Goodness of fit is like if you're present, or like your distribution and consideration.
Is it and historical, right? That was and. Okay, that's true. That's one reason we could use a goodness of fit. Give me something else you know.
Homogeneity is when you're comparing two distributions.
You're comparing two distributions. Well, you are in goodness of fit too, because you're comparing an observed one that you're currently to something before. So you are still comparing two distributions there. Okay, so you have one variable, right? So you have one variable, and you have two different distributions based on that. Okay? So I think that's kind of what you were saying, Hunter, right? As you leave. Yes, fine. All right, give me something else you know. What did you read about? What is independence? Yeah. Go ahead, Isaiah. Two or more. It could be more than two. Okay. So two or more variables in one distribution. Okay. So I like to use the Titanic example. It's a classic example of independence. There were many different types of tickets you could have bought on the Titanic. You had your first class, I don't know the classes. What were they? Third class. Was it just the three? And the crew. Okay, so you had 4 different ways to be on the ship, right? So those would be the variables, but you have one distribution, right? And you're looking at whether you lived or whether you died. So there is the kind of ticket would be one of the variables, and then whether you lived, your survival rate would be the other variable, okay? So you're kind of looking at comparing those two different things. And then you have the distribution of the different kinds of tickets and that kind of thing. So are the variables independent of each other? Is whether you lived or died, independent of what kind of ticket you had? And historical evidence shows that they're definitely not independent, because more people on the crew died, a lot more people on the crew died, and third class died than the first class tickets, right? We actually just read, I think there was just something recently, because it wasn't the Titanic, wasn't it like the anniversary just recently? It was just like 2 days ago or something like that, right? I read something about the pets. I didn't even realize that there were some pets on board the Titanic too, and they were only from the first class tickets. And only the little tiny dogs survived because they were able to ride on the boats out. The big dogs. Bye. That's exactly right. That's exactly right. All right. So anyway, so we have a different. What kind of data would we use for all of these? Categorical data. So we know that no matter what, we have categorical data. So anytime we are in this situation with categorical data, we know we are doing a chi-squared test of some kind, right? So that's where we're at. So we did goodness of fit before. We did that last time. We looked at a test distribution, A, B, C's, and F's, A, B, C's, D's, and F's maybe, I'm not sure, of a current class versus a historical population, or historical distribution. Sorry about that. So let's look at homogeneity and independence a little bit more closely. So don't write all this down, Okay, just kind of look at it for a minute. I'll highlight some important keys. But homogeneity is used to determine if proportions are the same in two or more distributions. Okay? It will look like a contingency table, so it looks like a two-way table. However, okay, it should represent two or more samples, like two or more different, like 2 years, for example. Okay, so you could have 2001 and 2015, and you're comparing those two different independent samples amongst one distribution. So you're comparing two samples to see if their distributions are homogeneous. Are they the same? And that's really what you're looking at. Okay? So it does look like it's a two-way table, but there aren't two different variables that you're comparing. Okay, it's two different samples, one variable. Right?
So it would have like a year or something, or
yeah, years is different years is a very common way you can do sampling. Yes. Okay, so look at the columns. Are they just, these are questions you want to ask yourself. Are they distinct groups where the data was collected separately, okay, in 2001 versus 2015? Definitely two separate independent samples. So that would not be it would not be a goodness of fit test because we had two distinct samples, not a historical one, but rarely just looking at two samples individually there. Obviously, I just said this, different years, we know it's homogeneity. Okay? If it's in an experiment, think about experimental design, okay? We look at a test of homogeneity to decide if the treatment groups differ from one another, okay? We have treatment that has a placebo. We have a treatment that has an actual treatment drug. Are they different from one another? That would also be a test of homogeneity. Okay, and we're actually going to look at an example of that here. If the question specifically asks something like, if it asks you a question in the problem, okay, the test for homogeneity would say, do the distributions differ? Okay, that would be a clue in the wording of the problem that it's a homogeneity issue. Okay, so that's kind of like the question to look for. So let's look at an example, and this is an experiment situation. And I want you to read it first, and then I want you to make sure we can decide, is it homogeneity, yes or no? Okay, so why is it homogeneity? We don't have two different years here, so that's a dead giveaway when you have two different years. But I have two different treatment groups. Actually, I have three different treatment groups, don't I? Okay, so because I have different treatment groups and I'm comparing the outcomes of those different treatment groups, this is homogeneity. Do people, were their results different from the placebo versus the St. John's wort versus the Posrex? Is that how you say that? Posrex? Oh no, that one. Okay. I like Posrex. I don't know. Okay, but we have a natural remedy, we have a prescription drug, and then we have a placebo. So we are trying to decide, is the outcome different? So I'd like us to be able to perform a chi-squared test for homogeneity and make a decision, yes or no, the outcomes are different. So let's make sure we would know how to do that. Let's go ahead and, well, we should name the test. Always name your test, because remember we've learned from looking at some of the grading rubrics from the AP that naming the test is part of it. So we have a chi-squared test for homogeneity. And we're going to do our null and alternative hypotheses. What do you think they're going to be? What's the null hypothesis? There is no difference in the outcomes of the treatment groups. Okay? I'm sorry, say it again? Okay, there is no difference in whether the depression returned for the placebo, the St. John's wort, and the Posrex. Okay. You should, because context is a deal, right? I'm just going to say 3 treatment groups, but you know to say placebo, St. John's wort, and Posrex. What would the alternative hypothesis be? There is a difference, and that's really all you know.
Now, would that count for if just one of them?
Yes, yes, because that would be a clear standout that is a better remedy than the others. Okay, so when we're looking at homogeneity, it means they're all the same. Okay, and which if one of them stands out, they're not. So there would be a clear difference. Okay, so we've named the question. Yes. Well, the outcome is the depression. So the outcome would be a generic term for any situation. So you really want to be specific about the context in this problem. I think that's kind of what Isaiah was saying to begin with. That's okay. No, it's okay. He caught me because I was doing what you were doing, and he's actually right. We should all follow him because he's right. That's good. All right. So what's the next step? Naming the test, state the hypotheses. What's next? Conditions. Okay. What are the conditions for any chi-squared test? Okay. So what are these collected randomly? Well, in an experiment, they don't come to us randomly. How do we deal with randomization in an experiment? We randomly put them in treatment groups. So it does say that in the problem, they were randomly divided into 3 treatment groups. So we've met that condition. So we should say subjects were randomly put in their treatment groups. And what's the second condition for all chi-squared tests? Which kind of counts? The expected counts have to be greater than 5. So do I see any expected counts? Nope. Those are all observed. Okay? So let me show you a shortcut. We will, next class, we'll look at how to find it using the long cut. Okay? There's a reason why we have to know how to calculate each of those cells, and we'll look at it in a minute. But for now, if we want, the calculator automatically generates the expected. You know, in the goodness of fit, you had to do it yourself, didn't you? You had to find like the 15% of the A's and figure out that number. So we found our expected counts by our own hand. But the calculator will do the expected counts for you. Yes, ma'am.
Okay, when it doesn't give you like a 15% or something else,
then you wouldn't be able to find the expected, and you wouldn't be able to compare it, because those percentages are the historical distribution that you're comparing it to. So if it didn't give that to you, it wouldn't be a chi-squared test anyway. Okay? All right, so because this looks like a two-way table, what should we do? Where should I enter? I can't go to list, matrices. So I'm going to go to matrix, okay? So if you go to matrix, and some of us may or may not have ever done matrices before because it's no longer in the curriculum. Okay? It used to be in Algebra 2. If you go ahead and look for underneath the math symbol, that inverse symbol on your calculator, it's second matrix. Do you see that? Tanner, find your calculator. We're doing matrices now. Second matrix. It's right underneath the math key. Do you see it there? Okay. So in the matrix, you're going to have these 3 options: name, math, and edit. Okay. Name is when you are actually doing something with it. We're going to be entering values in, so we're going to go over to the edit key and we'll hit enter. We have to tell the calculator the size of the matrix that we want, and it always goes rows by columns. So the first is the number of rows, and the second number is columns. So in this case, what size of the matrix would I need? 2 by 3. Okay, so 2 by 3. And if you get it wrong, the good news is that it will show up. If you did it the other way around, it wouldn't look identical, so you'd know what you did wrong, right? So it's no harm, no foul. All right, so let's just enter our values in here. We have 24. It goes across the matrix or across the row. We'll go to the second row and enter those values in as well. Questions, Zachary?
What would be the difference if you swap them? Like,
It would become long this way. It would, because the variables would be in the wrong place. So you just have to pay attention to that. So just, if you did it in the backward, just go and change it. Not a big deal. Okay? All right. So at this point, we want to go ahead. We know that we've told the calculator our observed values. It will automatically calculate the expected values. So we're going to go ahead and do the test, and then we'll come back and check that condition. Okay? I will show you, I promise, next class how to find it by hand, which will make a difference on some multiple choice questions that I've seen in the past. So what test are we going to do? If we go to test and we scroll down, I see the chi-squared goodness of fit test, but the goodness of fit test used the list, didn't it? It used list 1 and list 2. Since this is a matrix question, it's actually going to be the regular old chi-squared test, even though it's specific to homogeneity. All right, so we'll come back and look at this condition. We're telling the calculator we put the stuff in the observed, our observed values in matrix A. The calculator is telling us it's going to put the expected values in matrix B. Okay? That's fine. We'll go ahead and calculate. Okay, and it gives us everything we need. It gives us our test statistic, which I will show you in a minute how to find, or you probably already know. But I'll go ahead and write the answer. We'll write it out in a minute. Is 8.4. And the degree of freedom is 2. Tell me why. Devin has his hand up, so we'll ask him.
Define degree of freedom for like a consistency table with the number of rows minus 1 and the number of columns.
That's for independence only because the rows in this case they're the two different treatment groups. So the only variable we're really concerned with in this case for homogeneity is in fact the columns. Okay? So if we have two variables, I agree with you. Okay? Rows minus 1 and columns minus 1 is all for all? Hang on, now I'm second guessing myself. Well, 3 minus 1 is 2. That's what I was thinking of, but it would be times 1 anyway. It still works in this case. Right, but so but for all of them. So, but that's I think it's just rows minus 1. No, yes, but there could be different outcomes, so you got to be careful on that. I think it's just the rows minus 1 in this case. All right, p-value, and what do you think about this p-value? Oh, didn't want to write it there. Is it small or large? It's small. We're going to figure out how they got that p-value, by the way, because it's important. I'll round it. Okay. So am I going to reject the null or fail to reject the null? Reject the null, which means that what's true? We don't know which one, but one of them is different. There is a difference in the natural remedy, the prescription, and the placebo. Right? There's a difference. One of them works better than the others. Is basically what we notice here. Okay? So let's go through real quick and figure out how they got these numbers. Oh, by the way, shouldn't we also check our conditions? So shouldn't we check the expected counts? So let's go to matrix. How do I figure out what values are in matrix B? Well, if I go back to matrix and I go to edit and I go down to matrix B, they'll be there. Okay? So for our second condition, we should probably say that this is our expected, helps if I can write, our expected counts are this. Was what in the just checking? Right, right. Right, the ratio has to be the same. Right, exactly. So hang on. So let's make sure that we understand where this 20 and 10 came from. Do we? Okay. So let's look at how many people were in each group. Weren't there 30 in each group? Okay. So if there's 30 in each group, let's look again where the numbers came from. 30 in each group. We good so far? Okay, but where did 20 and 10 come from? Right, the ratio has to be the same. Why wouldn't we do 15 and 15? Things to ponder. Okay, there is a reason. I'm trying to think of. Hang on one second. Why is my brain not working today? Okay, I'm going to come back to this for a minute because, like I said, we were going to investigate why these are, and I promise you we'll do it next class, okay? I just need to think about it for a minute, and my brain's not working for, I think I'm too focused. Do you have an answer? Please tell me you have an answer. Shh. Yes, yes. What do you mean by even it out? Explain that to me. Okay, go back to this. Okay, shh, listen to Brian. From this? Oh my God, that's all I needed to know. Thank you. My brain is fried. So in this direction, they all add to be 60. In this direction, they all add to be 30. Do you agree? Okay. So 60 divided by 30, I'm sorry, 3, there's 3 of them. There's 60 divided by 3 is 20. 20, I'm sorry, this is 30, divided by 3 is 10. Why couldn't I'm like my brain is losing my. You were there. You just were doing too much math. But yes, so I wasn't working for some reason. Huh? That doesn't matter, right? The ratio has to be the same. Yes, that is true. Phew, that took a while to get there, but we got there. All right, so how do I find the chi-squared statistic by hand? Do you remember? What's the formula? Observed minus predicted divided by, squared, divided by predicted. Okay? You predicted, expected. Is it expected in your formula sheet? I'll be consistent. All right. In this particular case, you would have to do each one individually and then add them up. But because I would only make you do that by hand if you were doing a goodness of fit, okay? But in this particular case, it's okay to use a value that the calculator gave you. Notice that in the goodness of fit test, it gave you that contribute is what we figured out that mean, all the contributions, right? And if you go here, it didn't do that. Sugar. I would have said a different word, but I would have gotten fired. Okay. Right. Delete. But notice guys, notice the contributions to the chi-squared value are not given here by the calculator, which is meaning that they're not really going to ever ask you to calculate it by hand. Okay, in this case, but we know how we would find each individual one. Okay, you would find each individual cell, find its chi-squared contribution. All right, so we're going to reject that bad boy and go from there. Now, we are running out of time to be able to do the independence test, but I wanted to at least start it and give us a contextual situation for us to think about. Okay? We know when it's used, and on your homework you're going to be asked some questions about when do I use what test, and then I'll give you some other tests to try. I might throw in an independence one in there. The only difference for independence is now I have two variables on one sample that I'm looking at, right? The other one was two samples and one variable. That's the difference. So with independence, we have one sample, two different variables. The variables are their gender in this case, and whether or not their opinion on gun control. Okay? And so we're trying to decide, are those two variables independent of one another? Can you imagine what the alternative and null hypotheses would be in any null and alternative hypothesis, in any independence test would be? What's exactly the same? You don't say exactly the same. We're going to use the words in the test, so we're going to actually, in the hypotheses, use that word. So what are we going to say? Opinion is independent of gender. And then what would the alternative be? We would say not independent or dependent. We're going to use those exact words. Okay, I'm expecting the words independent or I'm expecting the words dependent. Okay, so opinion is dependent on gender. So again, anytime you are doing a test of independence, we are going to be looking for those words. Okay, independence always your null, and dependence always your alternative. I can say always. It's exciting. Makes me happy. Okay? That's what, to answer that, well, right, that's the alternative, right? Always going to be too. So what we would do is exactly the same thing that we did with the goodness of fit test. We're going to use the same functionality on the calculator. You're still going to do a chi-squared test. It's just that your hypotheses are different. That's really the only thing that's different. Cool, right? That's it. One quick thing, I'm going to leave this here. We'll come back to it and start it next class. But one quick thing, someone was asking me how to calculate this p-value. I forget who it was. Was it you, Devin? If you look at chi-squared test, this test statistic 8.4, you are always looking for the tail probability. There's never a two-tailed in a chi-squared test. It's only one-tailed because of its skew rightness. So you're going to actually do, and if you should try it, it's going to be the chi-squared CDF of your lower bound, your upper bound, and your degree of freedom, which in this case was 2. Is that right? Yep. Okay, let's see if we get that same p-value real quick. So if we go to distributions and we do the chi-squared CDF, 8.4 E99, degree of freedom of 2, you should get the same thing, and we do.
What's that?
Probability density function. It's an exact situation. It's just one. It's not a cumulative over time situation. Okay? Yes? So what you're saying here is that in order to get full credit, you should say this to prove why you're rejecting the null. Either this or the words, it's very small, would be enough. Because that's showing what you compared it to. I agree, absolutely. Guys, real quick, chapter 26 is your homework, obviously. I want you to be able to decide which test to use. So you're going to do problems 1 and 2 because it's literally which of the 3 goodness of fit tests. They each have A, B, and C, so it's 6 things, okay? Which tests are you going to use? I want you to do problem number 4. And I want you to do problem, let's do number 11 since it's our Titanic example. That's kind of fun. Hang on. I'm going to do one more. Oh, independence. And we're going to do Let's do 11 and 26. Oh, hang on. So we're going to do, not 11. I apologize. Shh, 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 shh. We're going to do 26, 25 and 26. Sorry. So those 5 problems, I want to make sure that that's the correct one, but I believe so. Okay? Good deal.